Hi there, grade 11s, and welcome to today's physical sciences lesson. And what we're going to be talking about today is stoichiometry, also known as, and what you probably call it all the time, mole calculations. Okay, so we're going to be doing lots of calculations, and this time they involve chemistry and not physics. So let's have a look at what I've got for you today. First thing, let's just have a quick overview, a little bit of a recap so you can make sure you know where I'm going with this. So what do we have in mole calculations? What are our main calculations? We'll start here, the middle, at the top, with N equals M divided by capital M. Okay, so most of you should know, and if not, hopefully this is going to jog your memory, that N stands for moles, number of moles. Okay, and the small m is your mass, and the mass is usually measured in grams. And the large M, this one, I'll bring it around that side, is known as your molecular or your molar mass. And that is measured in grams per mole. Okay, that's the unit if you need to. If you're going to use it as a ratio, then obviously it's got no unit. But if you're going to use it in most calculations, the unit is grams per mole. Okay, so that's the one way of calculating moles. The second way of calculating moles is when we talk about, or when we have gases. Okay, so gases are difficult to capture and to then put them on something that can measure them, so to weigh them. Okay, so we have a way of calculating the number of moles using the volume. And if you remember last week and the week before, the previous lessons, we've been talking about the behavior of gases and what they do. And so we know that the molar gas volume, and hopefully you remember this, in other words, the volume that a gas occupies, when there's 1 mole of gas and it's at standard temperature and pressure, that number is set, and that number is 22.4 cubic decimeters. Okay, so that is known as molar gas volume. So you've got your actual volume, which is the little v. So this one is your actual volume. And at the bottom, we've got our molar gas volume. And that is a constant value that is 22.4. Okay, so that's two different ways of calculating moles. One, if you've got the mass of something in grams. The other one is if you're working with gases, we can use molar gas volume. And the third calculation I've got here is concentration is moles divided by volume. Okay, so we know that moles, the unit of moles is mole. The volume in this case is decimeters cubed. Okay, so let's just remind you that this is volume. This is number of moles. Number of moles, and then C is our concentration. Okay, all right, so that's what we've got. Big breath, deep breath. The calculations are not so bad. Okay, I know people think moles and they start panicking. They really are not as bad as you think. So you've got 3, and we're going to learn how to use. If you're not sure about it, today we're going to make sure we get them 100% perfect. Okay, so you know exactly what's going on when you come to a test or an exam. But now I've got a few words to go with this overview. I want you to just have a look here. The first one is ratios. Okay, now what do I mean when I'm talking about ratios? You remember that when we have a chemical equation, we have to balance it. Okay, now the reason we balance it is because of various laws that we have in chemistry, and one of them being law of constant proportion. The other one is law of constant mass. So in other words, what I start with in terms of mass, I need to end with. Okay, so if I start with all my reactants combined, if I start with 10 grams, at the end, once there's been a chemical reaction, whatever I make has to add up to 10 grams at the end. Okay, and what scientists have discovered is that reactions happen in a ratio. Okay, so for example, let me put one down. Let's say that zinc is reacting with hydrochloric acid, and it's going to make zinc chloride and hydrogen gas. Okay, now if I have a look, I've got 1 zinc on the left hand side, 1 zinc on the right hand side. We're okay with that. but I've got 2 chlorines on the right, 2 hydrogens on the right, but only 1 hydrogen and 1 chlorine on the left. So if I balance, I now have a balanced chemical reaction by putting the 2 in front of the hydrochloric acid. Okay, what does that mean for moles? This is where ratio comes in. It means the following. 1 portion zinc reacts with 2 portions of hydrochloric acid to make 1 portion of zinc chloride and 1 portion of hydrogen. So that means if I'm working in molecules, it'll be 1 molecule. If I'm working in buckets, it'll be 1 bucket. Okay? If I'm working in tons, it'll be 1. Okay. What we're looking at though specifically, okay, those are just examples, but specifically what it means is moles. Okay, so my mole ratio, 1 mole of zinc will react with 2 moles of hydrochloric acid to give you 1 mole of zinc chloride and 1 mole of hydrogen. We need those moles. If we don't have that ratio correct, none of our calculations would make sense. Okay, and you wouldn't be able to do the reactions that we do in chemistry, in industry, to get the things that we need if we didn't have them correct according to our mole ratio. Okay, so the ratio is really, really important. Now the second word is excess, and I'm going to link it to the third term here, limiting reagent. Okay, excess means more than enough. In other words, or it could mean too much. Okay, your limiting reagent means that it limits. Okay, so it does not go to its full extent. Right. So excess and limiting reagent, those are 2 concepts that we need to know. Right, everybody, hopefully you jog the memory cells there, that you know what we're going to head into today, and the things like moles and concentration and volume, all those things are coming back. That's what we're going to be practicing today. So I've got lots of things for you to do. I'm just going to sit back and watch. So the first thing, moles. 2 moles of sodium, I'm looking at the top here, reacts with 2 moles of water to give you 2 moles of sodium hydroxide and 1 mole of hydrogen. Okay, and I've got some questions for you. So this is just to jog your memory, but I'll do them with you. So number 1, how many grams of sodium hydroxide are formed from 12.5 grams of sodium? And that should actually be a nice little question mark there. And then number 2, how many grams of water are needed to form 20 grams of hydrogen? And then number 3, how many grams of sodium hydroxide are produced if 0.8 grams of hydrogen is produced? Okay, so we've got 3 different questions here. So let's break them up into separate ones. Okay, so we're talking about calculating moles. So I've got my ratio at the top. Now I like to work with the ratio and to write it out separately. Okay, so I always do this. It's going to be a 2 to 2 to 2 to 1 ratio. That's my ratio. Okay, now hopefully while I've been talking, you've been scrambling around in your bag and you've been looking for your periodic table. If there isn't one on the classroom wall, okay, or one in the book in front of you, hopefully you've got one on a piece of paper, or between 2 or 3 of you, you've got access to a periodic table, because we need our periodic table. We calculate our molecular mass or our molar mass using the periodic table. All right, so the first question, how many grams of sodium hydroxide are formed from 12.5 grams of sodium? Now, some of you are going, but you've got grams and then you've got grams. Okay, remember they're part of 2 different substances. So I'm going to write down the information that we've got. So sodium hydroxide, I want to know how much. What do I have? Sodium, I've got my molecular mass, and we'll go look what it is in the periodic table now. I'm telling you it's 23, but we'll go and look. And I've got my actual mass, which is 12.5. Sodium hydroxide, don't know about grams, so mass, it's what I've got to work out. Molecular mass, I can calculate from my periodic table. All right, so let's go and find our periodic table. There we go. So I need to go across here. So if I look, sodium is over here on the left-hand side, and it's got a molecular mass of 23. But sodium hydroxide needs sodium and it needs oxygen, which is 16, and it needs hydrogen, which is 1. Okay, so those are the three numbers we need to remember. So here we go. Sodium is 23. Sodium hydroxide is going to be 23 plus 16 plus 1. So that is going to give me 24 plus 16 is going to be 40 grams per mole. All right. What do I do now? Now I need to calculate moles. But the only one I can calculate moles from is my sodium. So let's go. Sodium, moles equals mass over molecular mass. Let's extend this page. And my mass is 12.5 and my molar mass is 23. Now, hopefully, you can see that 12.5 is half of 23. But if not, let's just quickly go to our calculator and we're going to go 12.5 divided by 23 gives me 0.54. Okay, so here 0.54 moles. Right, now let's go back to our sum. What do we do now? Ratio. Good, well done for those of you who remembered that. I take my 0.54 moles of sodium and I now use it, put it into my ratio and see what happens. Because my ratios are the same for the first two, the moles that I use are going to be the same, right? The only one that's going to change is at the end is hydrogen, and here I am scrolling down looking for my calculator. Meanwhile, I need to go here for my calculator. 0.54 divided by 2 is going to give me 0.27. Come on, there we go. So here, this is going to give me 0.27. Okay, hopefully everybody's with me. 1 is half of 2, so that's why 0.54 is what I've got. That is double the amount of hydrogen that I produce, so I need half of that. Okay, so the question is, how many grams of sodium hydroxide? So how many moles of sodium hydroxide did I make? I made 0.54. So I take that value, and now I'm going to calculate. I'm going to go mass equals moles times molar mass. 0.54 multiplied by 40, and I go to my calculator again, and I'm going to go 0.54 multiplied by 40, and that gives me 21.6. So my answer here is going to be 21.6 grams. Right. Next one. How many grams of water are needed to form 20 grams of hydrogen? This is going to be exactly the same concept. Okay, so I'm going to do it with you quickly, and then we're going to go on to a different type of sum. So how many grams of water are needed to form 20 grams of hydrogen? Okay, how many moles is 20 grams of hydrogen? So we're going to go moles equals mass over molar mass. This is H2. So my mass is 20. My molecular mass of H2 is 2, because remember the mass of hydrogen is 1. So 20 over 2, this is 10 moles. Okay, so it's a 2 to 2 to 1 ratio. I've got 10 moles of this, means it's 20 moles of that, 20 moles, and 20 moles. So how many grams? Mass equals moles times molar mass. My number of moles is 20. Have a look. Number of moles is 20. My molecular mass. Oops. So think back. Oxygen was 16. Hydrogen is 1. And there's 2 hydrogens. So it's going to be 16 plus 2 is 18. Okay. So I think we're looking in the region of 360 here, but let's double check. We're going to go 20 multiplied by 18, and it gives us 360 grams. Right? Okay, so everybody with me? All right. Wow, we've had a packed first segment, but what we've got to do now, as we always do, is we've got to go to an ad break. So as soon as we come back for an ad break, I've got some more to stretch your brains. I will see you shortly after the break. Welcome back, grade 11s. And I said to you before the break that we are going on to a section where you're going to do all the work. All right, and that's exactly what's going to happen now. I've got a mole calculation for you again. Okay, this time it's using volume. Okay, I'm not going to show you how to do it because you know how to do it. The first section was to just jog your memory. Now I want you to do it. What I will do though is I'll be nice and I'll do this. I'll remind you of what the equation is, and I'll remind you that V is 22,4, and maybe I'll put the ratio because you might need the ratio. Okay, other than that, the rest of it you can do. I'm going to give you, I don't even think you need more than a minute. I'm going to give you a minute. So you need to work quickly to calculate this. So you've got a minute starting now. Okay, everybody, so that's your time up. And I know a minute's short, but these sort of sums are actually quite quick to do. And you need to be able to do them under a little bit of pressure in your test. Okay, so let's have a look at what it asks. How many grams of carbon are required to form 11.2 cubic decimeters of methane gas at STP? Okay, so what I needed you to do is to work backwards, right, using this equation. So my first thing is I need moles equals actual volume over molar gas volume. I need to know how many moles are produced. So it's going to be 11.2 divided by 22.4. And hopefully everybody's with me. You don't even need a calculator for this. This should be 0.5 moles. Okay, it's half a mole. Now I take that and I put it into my ratio. I've got half a mole. I use 1 mole of hydrogen and I need half a mole of carbon. Okay, so from my ratio, right, so I'm taking it from the ratio. I'm going to say that moles equals mass over molar mass. So mass equals moles times molar mass. 0.5, and my molecular mass is 12. Okay, if you're not sure, you're welcome to check. Carbon, it is 12. So here we go. Half times 12, so 0.5 times 12 is going to be 6 grams. Okay, easy. Now, let's test your brains a little bit because we're moving on. Concentration. So I've got here, solution 1 contains 2 grams of sodium hydroxide in 50 cubic centimeters. Solution 2 contains 2.5 grams of sodium hydroxide in 66 cubic centimeters. So what do we need to know here? 2 things. Concentration equals moles divided by volume. Right. The second one is that centimeters cubed to decimeters cubed. How do I do that? And we've spoken about this before. You divide by 10 cubed, and 10 cubed is the same as 1,000. Okay, So the question here is, which solution is more concentrated, right? And you're going to answer this one. I'm going to give you 2 minutes to calculate the concentration. So here's solution 1. Okay. And there is solution 2. And you have got 2 minutes to calculate the concentration for each one of them. And that 2 minutes is going to start now. Okay, everybody, that's your time up. And I know you're saying, oh, but there wasn't enough time again. Remember I said to you, you need to learn to work under pressure. So I am going to be putting you under pressure because these things you need to be able to do quickly and accurately. So let's start with solution 1. So solution 1, I've got a mass of 2 grams. My molecular mass, we did it right at the beginning. It's sodium hydroxide. Sodium is 23, oxygen is 16, hydrogen is 1. You add them all together, you're going to end up with 40. So my molecular mass is 40 grams per mole. Right, so what I need to do, I need to work out that moles is equal to mass over molar mass. Right, so I'm going to have 2 over 40. I think I need to extend my page here. And I need to go to my calculator. And this time I'll use my fraction. 2 over 40, and my answer is 1 over 20, which is the same as 0,05. Okay, so moles is 0,05. So I'm going to take that, and now I'm going to calculate concentration. So I'm going to put it just on the side here. I'll do it in a different color. Concentration equals moles divided by volume. So 0.05. And my volume, we said it was 50 centimeters cubed. So 50, and I've got to convert it. So times 10 to the minus 3. Remember, it's the same as dividing by 1,000. So let's go to my calculator again. I use my fraction again. I'm going to go 0.05. And at the bottom here, I've got 50. I'm going to use my exponent button times 10 to the minus 3. Okay, what does that give me? It gives me a concentration of 1. Right? So let's go back here. Mine is 1 mole per decimeter cubed. All right. So now let's compare with this side. I'm going to have the same thing now, but my mass is 2.5. My molecular mass is still 40, nothing's changed. So my moles is going to be mass over molecular mass. That's going to give me 2.5 over 40. Okay, so I've got more grams. I should be expecting a greater number of moles. Okay, so fraction 2.5, and at the bottom here it's going to be 40, and I'm going to end up with 1 over 16, which is 0.0625. All right, 0.0625 moles. So now concentration. Concentration is moles divided by volume. 0.0625 divided by 66, because this one is 66, yes. Remember, times 10 to the minus 3, I need to divide it again. I need to do my conversion. And I'm going to do it as a fraction again, 0.0625. And here I'm going to have 66 times 10 to the minus 3, right? And that's going to give me 0.946. Okay, equals 0.946 moles per decimeter cubed. Okay, which one is more concentrated? Compare 1 mole with 0.946 moles. So solution 1. Solution 1 is more concentrated. Right, everybody okay with that? So now, next one. It's a continuation. Still solution 1. What is the difference in concentration? Okay, so what's the difference in concentration? I'm going to give you a minute. There's no formula for this. This requires thinking. Right, I'm going to give you a minute starting now. All right, everybody, that's your minute up. Let's have a look. I said to you there was no set formula. You've got to use your brains for this one. You've got to think with a little bit of logic here. So what do we have? We've got solution 1 and we've got solution 2. And what we want to know is the difference in solution. So in maths, what is difference? Difference means subtract. So what I'm going to do is I'm going to go solution 1, which is the bigger one, minus solution 2. But what of those solutions? The concentration. So this was 1 mole, and this was, let's just go back quickly. This one was 0.946. So here I'm going to go minus 0.946. Okay, and I'm going to get an answer, because this one I don't think my head's going to do. I'll use my calculator. 1 minus 0.9946 0.054. So my difference in concentration equals 0.054 moles per decimeter cubed. Okay, so do you see that not everything has got a specific formula or a specific equation? Okay, a lot of this requires logic. Like when we talk about ratios, It's logic. So we're testing your thinking processes, okay? Not just can you use a formula, can you put the numbers in, but once you've done that, do you know what to do with it afterwards? What else can you do with it? Right. So here we go. This we're going to do, because we're going to go to an ad break again soon, but we're going to start this one and then we'll finish it after the ad break. This is one for you to do, okay? It's got everything added into it. 45 grams of magnesium nitrate is dissolved in a small quantity of water and the solution is made up to 500. Okay, so there's my final volume, right? I've got a mass, so that means there's at least 2 calculations there. Then my first question is calculate the concentration. And the second question is 150 cubic centimeters of solution is transferred to a new beaker. Calculate the volume of water that must be added to dilute the solution to 0.6 moles per cubic decimeter. Got a dilution question as well. So there are, if I think about it now, 5 calculations that we're going to need to do just to answer the sum. But don't worry, you can do all of them. You just need to be able to apply your logic so that you know the order in which we need to do them. I'll give you a hint. The first one is going to be this one. Okay? And then once you've done that one, the second one is going to be this one. Right. And once you've done that, we're going to come back to this one so that we can answer question 2. All right, but that is fun and games after the ad break. We're going to the ad break now, and I'll see you just after that so we can answer these questions. Right, everybody, welcome back from the ad break, and I hope you've got your thinking cap on because we're working, okay? And I gave you a hint before we started how to do this. I'm going to give you 2 minutes to answer the first question, calculate the concentration. Your 2 minutes is going to start now. Okay, everybody, that's your time up. So let's get going. So calculate the concentration. But we've got mass. So what does that mean? We've got to start with this one. And I did give you the hint. It's going to be mass over molar mass. So I'm going to do a few things in one step because there's other things that I want to show you. But you can do it in multiple steps if you want to. So let's just get rid of some of these. Okay, so we've got magnesium nitrate. So my mass of magnesium is 24. Nitrogen is over here, it's 14, and oxygen is over there, it's 16. Okay, so if I go back, I've got 45 grams of magnesium nitrate. So we said magnesium is 24. Then I'm going to go 2 times nitrogen. So it's going to be 14 times 2. And here I've got to go 2 times 3 oxygen, so that's going to be 6, plus 6 times, what is oxygen? 16. Let's just double check. I've forgotten. Goodness, can you believe oxygen is 16? Okay, you'd think I would know this by now. Plus 6 times 16. Okay, so let's work this out. I think we're going to need the calculator for this. Let's just put it on this side so we can have a look at our numbers. So I'm going to use my fraction. It's going to be 45 divided by 24 plus, what is this? 14 times 2, which is 28. 14 times 2, that one I know. Plus, you know, I like my brackets. 6 times 16. Come on, 1, 6, close brackets. Move my arrow. And I'm going to end up with 45 over 148. And if I work out the answer, 0.304. Okay, so 0.304 moles. And then concentration equals moles over volume. I'm going to have 0.304. And my volume, centimeters to decimeters again, remember, times 10 to the minus 3, or I'm going to divide by 1,000. And if I look at my calculator again, let's move it to this side now. Come on. Now I'm going to go 0.304, and down here I'm going to go 500 times 10 to the minus 3. And it's going to be 76 over 125, which is 0.608. Right, so 0.608 moles per decimeter cubed. All right, now let's see what else I've got for you. Same thing, okay, same question, but now question number 2 says 150 centimeters cubed of solution is transferred to a new beaker. Calculate the volume of water that must be added to dilute the solution to that concentration. So my original concentration is 0.608 moles. Do you see they're very close? Okay, so this is where numbers, C2, this is where your accuracy is important. Right. Okay, I'm going to give you a minute to work out that number or that volume, and that minute's going to start now. Right, everybody, so that's your time up. Let's have a look. So I'm going to do this, what we call the long way around. Moles equals concentration times volume. Okay, why am I doing that? Because whatever volume I take out has got a certain number of moles. That number of moles I'm putting into my new container. Okay, so I need to work out my number of moles. So it's going to be 0.608 times 150 centimeters cubed. So it's 150 times 10 to the minus 3. Let's put that in a bracket. And I'm going to put it onto my calculator quickly, and let's see what we've got here. So I don't want that. I'm going to go 0.608 multiplied by, I'll use my brackets again, 150 times 10 to the minus 3. Okay. And that's going to give me 0.0912. So my volume is going to be moles, 0,0912 moles. Okay, that's the number of moles I'm carrying over into my new solution, but it's got a different concentration. So now my C2 is moles divided by volume. I want to know what my volume is. Okay, what my new volume going to be. So volume is equal to moles divided by concentration. So my moles is 0,099. Let's write that again. 0,0912. I'm going to divide that by 0,6, and we're going to end up with a new volume. So let's go here. Move it across again. So 0,0912. And I'm going to divide that by 0.6, and I'm going to end up with 0,152. There we go. 0,152, 0.152 decimeters cubed. Okay. What does that mean in centimeters cubed? That's actually 152 centimeters cubed. Do you see the difference is only 2 centimeters cubed? Does it matter that the difference is so small? No, it doesn't. You just need to work with the numbers that you're given. Okay. Now, onto the part that does trick people sometimes. A limiting reagent or a limiting reactant. This is when there's not enough of a particular reactant to use up all the other reactants. Okay. If you have something that's in excess, that means that you've got more than enough. So you're either going to have not enough or you're going to have more than enough, right? So an example of this type of question is this. Aluminium reacts with chlorine gas to form aluminium chloride using the following reaction. 2Al plus 3Cl2 goes to 2AlCl3. Okay, so there's my ratio. The question is how many grams of aluminium chloride could be produced from 34 grams of aluminium and 39 grams of chlorine. Okay, this is the trick here. The ratio is important. I need to work out moles of both. So I'm going to start with the aluminium. Moles. So moles equals mass over molar mass. It's going to be 34 divided by, let's have a look here, periodic table. Aluminium is 27. So go back here. 34 divided by 27. Okay, and that will give me, go to my calculator quickly, 34 over 27. And that gives me 1.259. Okay, so let's make that 1.26 moles. Okay, if I go to my ratio, I've got 1.26 moles, right? I need to get that into a 3:2 ratio. In fact, let me do this. I'm going to rewrite my ratio down here because this is important. It's a 2:3:2 ratio. Right. Let me just work out the chlorine quickly, and then it'll make more sense. Moles equals mass over molar mass. It's 39, and chlorine, if I remember correctly, is 35.5. Yes, it is. So here we go. It's going to be 39 over 35.5 times 2, because there's 2 of them. And it's going to give me 39 over 35.5 times 2, which I think is 71, if I remember correctly. And that is 0,549. Okay. What do I get? 0,549 moles. Okay. So my first one, I'm going to go according to aluminium, right? I've got 1,26. Let's just see where the aluminium is. So this was aluminium, this is chlorine, and this is aluminium chloride. Okay, 1.26 moles. I need to convert that. So what I'm going to do is I need to, the way it works is I'm going to take the moles that I've got, I'm going to divide it by my ratio, which is 2. Okay, I'm going to multiply it by my new ratio, which is 3. And I'm going to get 1.89. 1.89. This here is 1.26. So what it means is that for 1.26 moles of aluminium, I need 1.89 of chlorine. Okay. If I go according to the chlorine, now why is this now not... come on, I want you to... It's 1.89. I need to extend my page here, but it won't. For some reason, this is fighting us, folks. Okay. And then if I try this again, right, there we go. Okay, let's do this. Come on, extend page. Right. My chlorine. My chlorine ratio, we said that we had 0.549. So now my value here is 0.549. Okay. I need to do the same thing as what I did earlier. I'm going to go 0.549. I'm going to divide it by the current ratio. And then I'm going to multiply it by my new ratio, which is 2. And here I'm going to end up with 0.366. Right? So, come on. 0.366. 0.366. Okay, what does this mean? This means the following. If I go according to the chlorine, if I use 39 grams of chlorine, I need 0.366 moles of aluminium, right? But I've only got 34 grams of aluminium, which means that I've only got 1.26 moles of aluminium. Okay, is that enough for the chlorine? The answer is yes. Okay, I've got more than enough aluminium if I use this amount of chlorine. But the other way around, if I want to use all of my aluminium, okay, if I want to use all of my aluminium, I need 1.89 moles of chlorine. Do I have that? No, I don't. I've only got 0.54. So what does that mean? That means that my chlorine is my limiting reactant. Okay, and it means that my aluminium is in excess. All right, now, please don't worry that we didn't get to every single type of calculation in today's lesson, because we've got some revision lessons coming up, and you've got plenty of access to your teachers, to other people, to worksheets, and I really encourage you to do those and do as many of them as you can. My advice is to try and do as many of these limiting reactant questions as you can, because those ones do come up in the end of grade 11 and they come up again in your matric year. All right, so thank you for working so well today, and I look forward to seeing you in our next lesson.